talks. We're really grateful that Zvi Bern has agreed to give a retrospective talk here in the middle of the conference. And I just want to emphasize that this is not in any way intended to say that this is the end of the journey. I mean, as you can see from all the talks we heard so far, we are in the middle of a long and wonderful voyage. But there has been so many things that have gone into that, and from so many directions of different parts of physics and mathematics, that we still thought it could be great if Zvi could give us an overview of how it all came about. So thanks again, Zvi, for doing this for us, and we look forward to hearing your talk.
Okay, well, thank you for organizing such a wonderful conference with so many great talks. So, of course, I was asked to talk about the early history of the field. The early history is relatively simple because there were relatively few of us working on it. In later years, of course, there's a much richer, much more complicated history. And I have to say, it never ceases to amaze me how many people are working in the field, how many new people there are. And I think the organizers had in mind that many of the young people don't know about the early years, how things came about. And one thing I'm actually really sorry about is that we can't be in Copenhagen, because in fact my story is going to start in Copenhagen. That's where Amplitudes began for me. I get the one thing I get the feeling about is that the young people, they think that people always worked on Amplitudes, that it was always some interesting field that people were working on from the time of Rutherford. But that's not exactly true. When I started in the late 80s, the general attitude was in the 1960s, well, people understood analyticity and unitarity, and that was the end of that. And then we had Feynman rules, and we're done. And what else needed to be said? Of course, as we know, that's not exactly correct, that there is a lot to say. And there's Amplitudes, this idea of amplitude has really blossomed and gone in so many directions that I'm not going to cover here. I'll just talk about the early history and lessons from the early history. I think some of the principles that we had in the early days are still applicable today. And there's all sorts of directions. There's the new formulations of fundamental physics. Nima gave this very energetic talk on fundamental ideas, thinking about physics in completely different ways, string theory, integrability, supergravity, super Yang-Mills, QCD, phenomenology. What we heard talks about SMEF, for example, which is not exactly QCD, classical gravity, and then, of course, gravitational waves, as in the last couple of years has become very hot and big. And then, of course, the connections to mathematics. And one thing that I want to emphasize is to kind of look back and just think about why we were successful, why things worked pretty well and the field is really thriving. And it comes from two parts. One is that there's structure, symmetry, beauty, aesthetics. That's what we're always looking for. We're always looking for a structure that we can latch onto. But there's another pillar that's really important. That's, I think, equal weight, and we really need to pay attention to. And in fact, we are paying attention, as we can see from various talks, is explicit results that are useful outside our field. Right? If we spend all our time looking in the mirror and admiring how beautiful we are, that's not good enough, right? We have to produce something practical, or the definition of practical is it's not just interesting to us, but it's interesting to other people, people who work on very different types of problems. And the question is, how can we help them? What can we do? And in fact, any field needs the support of both these pillars to thrive. We've been thriving now for I'd say about 20 years. And the question is, can we continue to thrive for another 20 or basically as long as you can, for as far as we can see. And for that to happen, it's the second part the explicit results that are useful outside the field. And the birth of the field, in fact, had a lot to do with that, looking at questions that were interesting to other people. Now, from the very beginning, the beginning of time, which I'll define to be the Parke-Taylor paper, there is a basic philosophy in how we think about things, and we continue to think about things, is first what you do is you do a new calculation by some means, whatever the best available methods are, or it could be any method at all. And what you do is you try to uncover some kind of a new structure, some kind of a pattern. It doesn't have to be theoretically profound, but maybe it's a pattern of some kind. And you use that to design some kind of new tool, and then you use the new tool to do new calculations, new structures, and you get a virtuous cycle. And one of the key priorities that I think that, the people that outside our field see is we spend a lot of time thinking about new and useful structures. And another part, which is of course extremely important, that since the beginning of time, defined as the Parke-Taylor paper, is to try to push the state of the art for quantities of physical interest. And there's many examples of structures, Parke-Taylor, of course, the twistor space, geometric interpretations, amplitude-hedron, the n=4 super-Yang mills, and how we link it to strong coupling and double copy and so forth. Now, where did it begin for me? Oh, that wasn't supposed to happen. That's supposed to be the Niels Bohr Institute. I didn't realize it was actually active. Anyway, that's the Niels Bohr Institute there. That's where it began for me as a postdoc. And David Kossauer was visiting for a month. It was actually Jan Ambjorn who invited him. And one of the things that's really great about the Niels Bohr Institute is the flow of visitors. So there I was a postdoc, and David was a postdoc at Columbia, and he wasn't working on anything of specific interest to the people at the Niels Bohr Institute, but anyway, he was invited for a month, and that's where I met him. And by the way, I should say that the Baumick Institute, once the pandemic is over, we're going to try to emulate more this idea of the flow of visitors. It's at least in my life, it made a huge difference. And David came and he told me about a paper they had written. This was with Lee and Parmeshran Nair on multi-gluon scattering, a string-based calculation. And they had done the 5-point tree amplitude. And yes, back in 1987, you could write important and profound papers on 5-gluon tree level amplitudes. Days were different back then. And what they had done is they used string theory directly, not Feynman diagrams, but string theory, which we can think of as an amplitude-based approach. First quantized string theory, that's amplitudes. And they incorporated ideas that had been understood earlier, Parke-Taylor, Spinor Helicity, color decompositions, U1 decoupling identities, and they made some progress in writing down some nice clean expressions. And the question that David and I were asking is, can we apply these types of ideas to loop level? And it certainly took us a while to answer this decisively. That was not so simple. One of the basic tools that we used is Spinor Helicity. And this had been around for quite a while, but it wasn't until the paper from Yu, Zhang, and Chang where it was really done very, very cleanly, the modern way we do Spinor Helicity. And that was in 1985. And finally, we had this nice, clean way to describe the physical degrees of freedom. And this was one of the basic tools that we've used since the beginning of time. And here's the beginning of time, the Parke-Taylor paper. One thing you can notice about the Parke-Taylor paper is that it actually does not have the Parke-Taylor amplitude, but we normally call the Parke-Taylor amplitude. It has what we should call as a Parke-Taylor formula, but it had the key idea that there's simplicity for arbitrary numbers of legs, right? And this is the key idea of amplitudes that drives the rest. From that day forward, those of us who work on Amplitude, we all believe that there's simple structures, much, much, much simpler than you could possibly guess from Lagrangians, from any kind of Feynman diagrams. And that was contained in their paper. This is the squared amplitude, and you see here this usual form, which you can write in a better way in terms of spinors, which came a little bit later. And there were some key lessons there, the key lessons that we should all be thinking about to this day. First one is you can guess further than you calculate. Yes, in those days, 6-point was really hard. 6-point tree level was really hard. And they couldn't even do it analytically, they did it numerically. But that was good enough to verify that they had the right formula. The other point that they had, which we use today constantly, is the analytic structure is very powerful. If you understand the factorization properties, how the amplitude behaves as you go towards a pole, you can verify a lot. And this is one of the key checks they had on their formula. And probably the most important thing that drives everything is amplitudes can have remarkably simple structures hiding them, and you should look for them constantly. Every time you do a calculation, you should ask, what can you learn from it? They had done 4 and 5, and then that was enough to start making guesses. So it was 34 years ago, David mentioned to me the Parke-Taylor Formula. And I hope you forget what I said, but anyway, I said, what's that? I didn't know. Anyway, David Kosauer said the right thing. He said, everyone needs to know the Parke-Taylor Formula. Anyway, David is right. 34 years later, it's true. Everybody knows it, not just in our field. And there it is, the work of art. Now, you'd think that when people saw this, they'd say, oh, this is great. Oh, I got to work on this. But of course, that is not at all the way it worked. What people could see is that there are many flaws. And the key flaw with the Parke-Taylor formula, with this amplitude, is that it was too special. It only worked for special helicities. If you're interested in collider physics, you can't say, oh, I have some of the helicities, right? You have to have all of them. You have to have the entire amplitude, all configurations. This was only massless. It was only tree level. It was not proven. What's it good for? What can you do with it, right? Those are some basic questions. Now, some of us were young and we didn't really appreciate any of these problems or concerns, but we could see that this formula was beautiful. And that was sufficient to keep us going, to start really thinking about, to take seriously that there's magic in amplitudes. And I have to say, in the early years, when people would ask what I'm working on, I never say amplitudes, because every time I'd say something like that, what would happen is, wasn't that all understood in the 1960s, right? And then you'd have to start explaining. So in fact, I would say, oh, I work on QCD, because at least QCD was respectable. It was a respectable field. And these different problems, it certainly took a while. Now, one of the key advances, which is still important today, is the Berends-Giele Recursion relation. So it's an iteration. What you do is you write down a current, it's one leg off shell, the rest on shell, and you can solve this recursion equation. The solutions for these currents they're given right here. This was extremely important for proving the Parke-Taylor formula, the MHV formula. And the other thing it showed is the importance of recursive approaches. That, of course, later on, as we know, on-shell recursion came, but the seeds are planted right here. And now, it turns out that this approach was very, very good for proving on the Parke-Taylor formula. But to go beyond that was actually quite hard. it was not a clean analytic approach. Numerically, it's still very fast. I believe it is by far the fastest approach numerically. That has to do with the fact you can cache intermediate results, but at least analytically, it was not so easy to use this. Oh, and here's the Bible. So in 1990, Mangano and Parke, they wrote a review, and this was our Bible, the guidebook for the next 10 years of what we needed to do, what the basic tools were. And this was tree level. These are multi-part on tree level amplitudes. And of course, this laid the foundations, all the important ideas of helicity and color. It was all contained in here. And it's a great review. If you haven't seen this, there are much more modern reviews, but if you haven't seen this review, you should have a look at it. So there was our first paper. So we had this idea that we were going to apply these ideas that were already looking successful at tree level. We were going to apply it to loop level. And we wrote this paper. I was still at the Bohr Institute. And what we did was we calculated the QCD beta function using a string approach. I have to say this was not particularly well received. It's hard to impress anybody by repeating a 15-year-old calculation. That's a theme you're going to see. You need to get to the state of the art before anyone pays attention. And in fact, there were all sorts of objections. We had trouble getting a paper accepted. For example, string states won't decouple. Infrared divergences are different in string theory than in field theory. And if you're wondering what the heck that's about, I don't know, because it's just not true, but never mind. People would say things like that. Or how can you get a beta function? It doesn't make any sense. Everybody knows the string is finite. You can't get a consistent string theory with SUN. That was another objection. And for QCD, we need SUN. Modular invariance is broken. And you could say the real objection was, can we do anything state of the art? And this was not a simple project because to deal with each one of these issues, it took a while, especially the issues with the string, the modular invariance. There were non-trivial issues. But the way you settle any type of debate, and we use this in our gravitational wave calculations, is just do the damn calculation. When you do the calculation, we reproduced a result from Ellis and Sexton 1986 paper on next to leading order 2-to-2 scattering in QCD. And yes, in 1986, state of the art was one loop, 4 point. That was a big deal. And anyway, we were able to do that. And one of the key lessons, you could say, for the young people or for everyone is you should certainly listen to objections, but sometimes it just go forward. And you have to think about the objections, but after a while, just go forward. And if you want to make any headway arguing with people, don't start arguing about modular invariance. Just get the answer and confirm. Do it in a way that it's absolutely clear it was done correctly. Okay. And there's the paper. One thing that we got was a much simpler form of Ellis and Sexton. It's actually pretty amazing how clumsy the Feynman diagram calculations were at that time. A lot of the modern tools were just not available, and it was actually quite difficult to do that. And this time, people paid attention because we had the goods, right? We had a state-of-the-art calculation. And in particular, Al Mueller and Zoltan Kunz, they were really great. They were very supportive and excited about this. And finally, we got a little bit of respect on modern approaches, or on maybe I should call them oddball approaches. And one of the things we noted was that at least some of the helicities were just absolutely astonishingly simple. This is identical helicity, amplitude, and this is in QCD. for any number of fermions, also scalars if you want them, and it's very compact expression. And the other helicities were also not too complicated. They were a little more complicated involving logarithms, as you might expect, but still remarkably simple. Now, after that paper, we joined forces with Lance Dixon, and that was really great. We really had a lot of fun working on this. And by the way, when I'm talking about the history, and I'm talking about our work, well, there weren't other people working on it in those days. It was quite a small field, a micro field. But we believed, we had Parke-Taylor to guide us. We believed that simple things would be found. But in any case, one way or the other, if you think you have a good method, not only do you have to do state-of-the-art, you need to go beyond state-of-the-art. That's the argument that works, that you're on the right track, not only for other people, but for yourself. How do you know that your techniques are really as good as you claim them to be? You got to do the calculation, and you got to go to the next order. You have to go beyond what people have done. And that's what we focused on, one loop corrections to 5 gluon amplitudes. And what do we find? And what we found is simplicity, especially in supersymmetric amplitudes. And one thing we noticed is if you organize the amplitudes into supermultiplets, pieces were simple. N equals 4 super Yang mills. That's right here is the N equals 4 super Yang mills 5 gluon amplitude, 5 external gluons and the N equals 4 multiplet in the middle. And that's quite a simple result. And so simple that it was clear that there was more to be done. And in fact, this was the first one loop 5-point amplitude in QCD that had been computed. And we understood supersymmetric decomposition. And by the way, all of this, it's data driven, right? You do the calculation and then you look at the answer, then you observe things. You observe supersymmetric decomposition, you observe that supersymmetric pieces are very simple. Okay. And finally, I'd say they started paying attention to us, the QCD people, like really paying attention, although I think they still thought we were pretty weird. And this was actually used later by Bill Kilgore and collider predictions, 3-jet production. So finally, we got the phenomenology. Now, question is, why is it so simple? And this is a key lesson. You do a calculation, however you do it. It could be a good way, it could be a rotten way, but you have an answer. And what you do is you just inspect the answer, and you just look at it. Just like Parke and Taylor, right? You look at the answer, and you notice it's really, really simple. So you go, wait a second, there's got to be a better way. Right? And what's the source? What's the better way? Well, we had our string methods, but clearly this answer was much simpler than we expected. So we started thinking about analytic properties. We noticed that this has very simple analytic properties, and we were looking at unitarity. Seemed like a good idea. Factorization. Factorization is the same idea that Parke and Taylor had used. You look at what happens in the collinear limits. It's a little more complicated at loop level, but you just look at that and you use that as a way of trying to build new amplitudes. And this pointed to much, much more powerful methods, right? And it all comes not by thinking about more powerful methods, but by looking at the answer. You look at the answer, and the answer then tells you that there must be more powerful methods. Okay? And that's a key lesson that, today we all know this, but however much we know this, we need to think about this more. We're always supposed to be doing this constantly. And there's our paper where we realized that because the analytic structure is so simple, we could bootstrap to arbitrary numbers of legs in N equals 4 super Yang mills. But that one was simple enough. Now, we didn't have on-shell recursion, right? This was the poor man's version, or we didn't have more modern, powerful methods like the quadruple cut. But the basic idea of using analytic constraints to find new results. And here's how it worked. And the cool part is we finally had the answer of what are Parke-Taylor amplitudes good for? Well, the answer is to generate more amplitudes. And the idea was by looking at unitarity, you can look at the product of tree amplitudes and look at like unitarity cut. And what you notice in the unitarity cut, if you feed in a Parke-Taylor amplitude, is that the loop momentum only appears in a few of the propagators. Most of the propagators don't know about the loop momentum. And that meant that a hexagon integral, which was a challenge, but a hexagon integral was all you needed in order to do endpoints. And that was very cool. So there was MHV, like the analog of the Parke-Taylor amplitude for n equals 4 super Yang mills, arbitrary numbers of legs at loop level. So now we were completely sold. By this point, we were true believers in the sense that there are structures here and you could keep on going. So we were thinking, great, okay, let's go apply this to QCD. Well, the next process up on the list of QCD, using the analytic properties, this new way of thinking about things, that was E plus E minus to 4 partons. And the basic ideas we learned from our calculations in n equals 4 super Yang mills. And in this paper, we discovered that, in fact, it was quite hard. And the basic stumbling block on using the analytic properties was our integration methods were not yet developed as they would be later. And if you tried integrating the QCD expressions, which had higher powers of loop momentum, you'd get quite complicated expressions. And so it's a problem of integration. And we didn't really know how to clean this up. And it took enormous effort to clean up. Nevertheless, we understood some of the basic ideas. We understood generalized unitarity, and we understood the key importance of the analytic properties. But as it turned out, our friends in QCD, they were not sitting still, Campbell, Glover, and Miller, they were competing with us quite well. And they were using traditional methods. And I have to say, I found that quite disheartening. Here we had what we thought was the greatest method of doing things, but in fact, it was hard. And not only that, traditional methods could do very well. So that was quite disheartening. Anyway, I went to a conference and I bumped into the hallway. I met Nigel Glover, and he said, unbelievably, he said, I really like the way you did it. Our methods have no future. And I have to say, I was very taken aback by that for 2 reasons. One is, I think that's probably the only time in my life I'm ever going to hear anyone say that their methods are somehow inferior. That just doesn't happen. But also because I didn't really appreciate what we had, right? Even to me, it wasn't absolutely clear of what the future would be. I mean, we had compact analytic approaches, but there were still some problems with it, like with the integration. That integration problem would only be solved later. And I couldn't quite see how this would all work out and how powerful the method would eventually become. But apparently Nigel saw it before I did. And it took a while to appreciate that. Now, let's talk about gravity for a little bit. So another direction was gravity. And the start of that was the paper from Kawai, Luong, and Tai. And that paper, it had a really astonishing idea in it. It said that you can get gravity from gauge theory directly. And it's an enormously powerful idea. It basically says gravity is no more complicated than gauge theory. And this was perfectly aligned with amplitudes. It was the amplitudes way of thinking. This was string theory. String theory at the time was amplitudes based. Everything was a first quantized amplitudes approach. Now, this paper did not get much attention. There was another Kawai, Luong, and Tai paper, which was much, much more famous at the time. This one was basically ignored because no one cared about field theory. Personally, I was quite mystified by that because it said something that you couldn't see in a million years by looking at the Lagrangian, at the Einstein-Hilbert Lagrangian. Or how could this be? And it's certainly a lesson, and sometimes it takes the significance of something, it takes a while for it to be properly appreciated. And there, of course, is the famous Kawhi-Leonti relations. It takes us from gauge theory to gravity through very simple formulas. You can do this at arbitrary numbers of legs. This was appreciated by one group very quickly. That was Berends-Giele and Kaif, 1988, so it was just a couple of years later. And they said, if you have the Kawhi-Leonti formulas and if you have Parke-Taylor, why not put it together? And that's what they did. And they just guessed it. They did numerical analysis up to 11 points, but essentially just by working out examples, they were able to get enough data to just write this thing down in the spirit of Parke-Taylor. Again, they understood soft singularities. So the same way that Parke-Taylor did it. And once again, this is just another example of guessing. The way we want to do amplitudes is we want to calculate and then we want to guess. For us, this was much later, it was 10 years later, we went back once we understood how to do QCD at loop level, and we understood how to do n=4 super Yang-Mills, then obviously based on this paper, you just go ahead and try to put it into loops. Our first attempt, that was, you can see that's 10 years later, 1997 and 1998, we realized, well, at 2 loops, n=4 super Yang-Mills is pretty simple. And therefore, supergravity, n=8 supergravity has to be just as simple, right? It just follows from the logic that we have unitarity in order to construct the amplitudes, and we have Kawhi along the tie to help us. So the idea is now you could import these simple ideas that you see in gravity, you could, in gauge theory, you can now import them into gravity. And it was just a bit later that, in fact, we even knew what the values of these integrals are. Now, something else that we tried is arbitrary numbers of legs at one loop. You'd figure that, well, if you could do gauge theory arbitrary numbers of legs, you should just be able to go ahead and do gravity. But as it turned out, this was quite a bit harder than we thought. We struggled with this for quite a while. And in fact, that there was a point at which I had a loss of faith. I never told Lance about this because my faith was restored before I told him. And the loss of faith was very simple. Nobody cared about scattering amplitudes. It wasn't that interesting. Now, maybe they cared about scattering amplitudes for colliders, but beyond that, certainly no one cared about gravity amplitudes. What were you going to do with it? And any idea, oh, we're going to use this for gravitational waves, let's just say that insight didn't come for another 20 years. So there was no relevance, no reason why you should really be doing this. And the question is, why am I working so hard on something that no one cares about? And I started really thinking, I should tell Lance, look, I've had enough, the problem is too hard. But a simple epiphany came to me. And that's just stepping back. And if you can work out a one loop all n gravity amplitude, just do it, like in the Nike commercial. Right? You don't ask what's it good for, who, what people care about it. That's not important. You just do it. This thing is magic, right? You're thinking about how would you do it with standard techniques. It's impossible. You can't even begin to even think about this problem. And here we had, it was within our reach. As it turned out, it took about 1 year and 5 minutes to figure this out, how to do this. And I think the key lesson even though I keep on emphasizing, oh, we need to do things that are relevant for other fields. We need to think about things that are of some experimental significance. In some cases, never mind that, just do it. And there was our paper. We finally did it. And if you're curious what the 5 minutes was about, it was the realization that these functions that we called half-soft functions, they contain the soft singularity. And we understood once that it needs to come in this quadratic form, then it was very easy to figure out what the correct answer is. And there were no fancy modern tools like quad cuts where you can just write this thing down. This was done by guessing and then verifying it by other means. And we got identical helicity for pure gravity. That was a very cool approach, a very cool thing. And then we also got n equals 8 supergravity, the MHV. And you might notice these things are very similar, and there's something very deep about that, which I won't get into here, the similarity between these two. But there it is. The simplicity continues. Our faith that there are simple things to be found at loop level, that simplicity continues. You could say the path from Parke-Taylor just continued. 2004 was a special year. That was the revolution. I consider that a singularity, the before and the after. Ed wrote this paper, Perturbative Gauge Theory is a string theory in twistor space. And this involved the twistor transform. I should mention that Nair, about a decade earlier, had a precursor to this. And what Ed had shown, argued, is that QCD scattering amplitudes, that they are directly related to topological string theory. And what had happened is David Kossauer had given a talk at the Institute. And afterwards, Ed came up to him and said something along the lines that he'd been thinking about some problem in amplitudes. And there was something in David's talk that helped him understand something. Well, as it turned out, at that time, we were organizing KITP Collider workshop. So I figured, what the heck? Let me write to Ed. And I invited him. And of course, he wrote back and he said, I don't think so. I'm not ready. And then a month before the workshop, he sends me an email which said, I think I have something of some interest to your workshop. Okay, so he was coming. Now, Ed, by the way, is not someone who's going to go to Santa Barbara unless he has something important to say, right? It's not to meet his friends in Santa Barbara. Ed's paper, and Ed, it was an earthquake. It was a meteorite strike and shockwaves till today. And anybody who was nearby, Roybon, Spradlin, Bolovich, they were postdocs at the KITP, and they got swept up into this vortex. And this was the moment, the before and the after is, before this, amplitudes was not a respectable field. That was stuff from the 60s, right? And not very interesting. After this, it was respectable. From then on, I would tell people, I work in amplitudes. Before that, I'd say something else. And what Ed found was perfectly in line with our philosophy. We're looking for structures. He found structure. What he conjectured is that in twistor space, gauge theory amplitudes have delta function support on curves of a certain degree given by the number of negative helicities and the number of loops. And there were two pictures, something called the connected picture and the disconnected picture. And this was really absolutely fantastic. I thought this was the greatest thing I'd ever seen. But as it happened to be, I was wandering the halls of the KITP at the time during the workshop, and I bumped into David Gross. And David Gross had Ed's paper in his hand. And he said, I don't think this is up to Ed's usual standards. I'm going, what the heck? I couldn't understand that. Anyway, I went back to my office and I started thinking, oh, what the heck did David Gross mean by that? But with a little thought, it became clear what the issues were. One is, you look at Ed's paper, it's a little vague. There are these curves in twistor space, and they're connected to amplitudes, and amplitudes have support on them. But first, there was no formula, no specific formula. And the other problem, which is much more serious, I think this is the one that was really bothering David, was that what do you do with it? There's all this great beauty, but what are you going to do with it? Anyway, those issues were answered. There was one answer. This was the RSV formula. And what this did is it turned Ed's words, you look in his paper, there's a lot of words about curves, and it turned it into a formula. There's a formula. That's a formula of great beauty. It's really a remarkable formula. This formula, it generates amplitudes, which are identical. They're the same thing as the amplitudes in gauge theory. Okay, now they had many checks on this, but if you look at the formula and how it works, it's completely different. It's like a meteor. It came from who knows where. It came from outer space somewhere, a formula like this. In my wildest dreams, I would not imagine that there could be a formula like this for a gauge theory, and there it was. And now, the value of this, the practical value of this formula is still unclear. It's really remarkable, and I think a lot more progress on understanding this, it's possible in the future. Something with this great beauty, you think there'd be a real application, that you could really learn some basic physics. At least this thing planted the seeds for CHY. And I think it's something that people should look at. You can go back and look at this very beautiful paper. Now, when this paper came out, this is Cachazo, Sverchek, and Witten, MHV vertices and tree amplitudes in gauge theory. I saw David Gross. I told him one sentence about what this paper is about. There it is. Tree amplitudes in Yang mills can be constructed from tree graphs in which the vertices are tree-level MHV scattering amplitudes. Anyway, David flipped in about 2 seconds. Instead of not up to Ed's usual standards, he was enthusiastic, right? If you got the evidence, you got the data that backs up, the usefulness, David had no problem. The twistor evolution had landed. And this is really great stuff, because first, it was very simple. I mean, there were Parke-Taylor, right? The essential core of simplicity. You can now use it. It wasn't just some pretty formula. It was something that was actually useful. And even our QCD friends, they loved it. And many people in QCD started working on this. Nigel Glover, for example, was one of them. And its practical use was very clear. It was something like Feynman rules in the sense you could assemble things, right? There's an assembly instruction, but it was much simpler, for example, to do the 6-gluon amplitude, instead of it being some state-of-the-art calculation, as it was a decade before, you just write down the answer. As fast as you can draw these pictures, you can write down the answer. Absolutely remarkable. Very easy to use. That's another thing that's actually an important lesson. You should always think about doing things, if you can, which are easy to use. And of course, many other things happened, which I'm not going to go into any detail. The most famous of these is the recursion relation, on-shell recursion. And this way, the building blocks are other amplitudes. You want new amplitudes, you use old amplitudes in a recursive manner. And very remarkably, this was inspired by not thinking about the problem of how do I do tree-level scattering in the simplest way. This was inspired by data. We had one-loop amplitudes, many examples in N=4 super Yang mills, which then fed back into this construction by thinking about quadruple cuts, thinking about infrared singularities. And actually, kind of amusingly, we understood how to, at loop level, we understood how to build recycle amplitudes, tree amplitudes into loop amplitudes before we understood how to recycle tree amplitudes into tree amplitudes. But in any case, we now had a technology, a general technology for doing amplitudes. But there was one part missing, and that was the loop integration. And that problem was solved around 2007. There was Brito, Cachazo, and Feng, and then there was OPP group and other papers. And there was Darren Ford's paper. This is the one that we use in our work. And this gave us a simple way to actually deal with the intervals. And that meant lots of things could be done. And that brought about what was called the next to leading order revolution. So this is a slide from 2010 from Gavin Salam, where he started using the word the next to leading order revolution. And you can see how much effort went into doing these QCD calculations. A 2-to-1 process done in the 80s. It took about 10 years to get to a 2-to-2 process. Right around 1990, 2-to-2 is still a big deal. And then 2-to-3 processes, another decade. Okay, and then here came the let's say 2-to-4 processes. Okay, and you might say, well, okay, what kind of revolution is this? This called Unitarity revolution, when in fact it took us a decade. And of course, the answer to that came a little bit later. That's 2 years later. There's Gavin Salam again giving another talk. And you could see 2-to-4, 2-to-5, 2-to-6 all came together. And then, of course, since that time, the past decade, people have been working at much more complicated processes, not just next to leading order. We heard all these talks about next square leading order, next cube leading order, and you could say the revolution continues. Now there's one thing I want to show you, which I think is pretty interesting, and that's about curiosities. And this is, I think, something very important to our field. And I think all of us know this, but it's, I think, always good to emphasize the importance of tracking down curiosities. And I'll show you 2 examples of that. Now, one of them is the idea that 2-loop 4-point amplitudes in n=4 super Yang mills, that they look like 1-loop square. And this is a bit of a curiosity. It's an observation. It's data driven. You do a calculation, you look at the result. And then another one would be there's some kind of similarity between planar and non-planar integrands, and what it means and what the consequences are. So this was now in 2003, and with Babis Anastasio, and there's Lance and David as usual. We were thinking about looking at 2 loops, 2-loop in QCD, and we were also thinking about n=4 super Yang mills, and we had worked this amplitude out. And then what we did is we guessed based on that, we guessed endpoint MHD, and then we proposed resummation to all loop orders. Now, how did that go? Well, this is just an observation. You do the calculation, you do it in terms of the polylogs, and you just observe. It's an observation that the 2-loop 4-point amplitude could be written in terms of 1-loop square plus a linear in 1-loop times some kind of a function. This had something to do, we recognize this as something to do with infrared singularities. That's the cusp anomalous dimension. And based on this, right, there's a little pattern here, right? It's a curiosity, right? This is like a little nothing, right? It's a curiosity that you can do this. We proposed that we could resum not only all loops, but all legs, at least for the MHV case. And at this time, well, there was only one other example of something like that, and that was the cusp anomalous dimension. And needless to say, we got a kind of frosty reception There was David Gross with David Kossauer giving talk at the KITP, and David Gross says, "So what?" And the basic problem is pretty clear. Based on this little meager evidence, you're going to somehow going to suggest that not only can you resum it, do all orders, all loop orders, is based on this little meager thing. And then on top of it, you're going to use it for something. When I gave my talk, this was at Lake Arrowhead, things went even worse. The basic problem was that n equals 4 super Yang Mills is a conformal field theory, and therefore S matrices make no sense. So there, what are you wasting our time for? Now, I have to say, years later, I go to conferences and I hear people very casually say, as everyone knows, the only observable is the S matrix. And I can tell you, back in 2000, people didn't know that. Anyway, our boldness, it seemed really crazy. And the question is this an accident? Now, one of the things about curiosities is you have to understand the curiosity very well. And there's a judgment call. Is this an accident, or is this something very profound? And this is the question you have to ask when you see something like this. Now, we understood the nitty-gritty of how exactly this works. And there was no doubt, absolutely no doubt in our mind that this was not an accident, that there was something here. Of course, we couldn't tell exactly how far it would go, or what exactly it meant, or where it would break down and so on. But it just no way that this could be an accident. It involved too many non-trivial identities and conspiracies in the polylogs for this to happen. So there had to be something here. Now, by this time, I learned very, very well. We'd all learned this. You don't argue with David Gross when, in fact, what you should do is, of course, just shut up and calculate. Right? If you have a bold prediction of some kind, you should provide some evidence. Right? It's as simple as that. David is, of course, absolutely right. Well, we needed to get more evidence. Where do you get evidence from? Of course, the answer is 3 loops. Now, 3 loops, we didn't have the integral, but as it turned out, I went to a conference. This is one of Blumlein's conferences, where Volodya Smirnov gave a talk and said, "I have this integral. Does anyone need it?" That was this triple box here. Well, anyway, I met Volodya afterwards, and I said, "Yeah, we need this one." And also on a napkin, I drew this integral, which I understand he has that in his apartment in Moscow under some glass, this integral. And it took a little while to do. In those days, there was no computer assistance. Doing the integrals was not easy. But anyway, after some amount of time, indeed, we had the answer, and we indeed found that it exponentiated. And this formula that you see here, there are some complications having to do with infrared singularities. Thanks to a paper by Magneya and Sterman, we understood everything about the infrared singularity. So that we could take care of. And now we had 3 terms, or in a sense, 2 terms, because maybe the first one doesn't count. So now we could resum. And indeed, we wrote down an ansatz. This is the BDS ansatz. This is for the finite part in terms of the cusp anomalous dimension. By the way, notice how lucky we are. The object that we needed to all orders and coupling, the complete answer for it, the non-perturbative answer, was known. And it was exactly the only one that was known, the cusp anomalous dimension, was exactly what we needed. And then we could have an ansatz. And then it took a little while before people appreciated this, because there was still this problem that we were talking about the S matrix, and the world was talking about operators. But anyway, Alda and Maldacena, they confirmed this at 4 points using string theory. 6 points, the guess is wrong. I mean, sometimes when you make bold guesses, you're not completely right. And this is, of course, fixing this, fixing our guess. That's, of course, still a very active area of research. And in a sense, the part we did is the trivial part. The parts that are being done today are much more complicated. Here's another example, which actually I'm very proud of. This is 2006. There's another curiosity. And this is copied. This is the exact slide I used in 2006 at a QCD conference. And the question was about going onwards. We understood a lot by then about one loop, and we wanted to go to higher loops. And the question was about simplicity. I mean, that's something we were focused on, maybe not so much the QCD people. And well, we noticed something. One of the QCD amplitudes, the identical helicity at 2-loop, it had a structure, a little curiosity. And the curiosity is that the planar integrand, this is written in terms of the -2 epsilon dimensional component of the loop momentum. Anyway, it's written in some special form that this planar piece is almost the same. It's identical for some part, these double boxes, identical planar and non-planar. Now, if you know about the inner workings of how this comes out, it's too fantastic to be an accident. There are some other parts here which they didn't fall into the pattern, some extra pieces. And this is always very tricky. When you see something not working, you have some idea that there's some relation, and it doesn't work. You have to make a judgment call on whether the part that doesn't work is important or unimportant. Anyway, I said, why do they look the same? I believe this is a clue. And needless to say, this landed with a thud, because a clue for what? A clue, okay, a clue, but for what? Certainly the audience was not impressed. And I didn't know what this is a clue for. I just knew it was a clue. And the answer came later. A much better place, simpler place to get data, n = 4 super Yang-Mills theory. Off at 4 loops of all places. So this is, we were working with, this is with, there was JJ, and there's Henrik, and there's Lance, and Radu, and we were working on n = 4 super Yang-Mills at 4 loops with the idea of looking at gravity as well. And we noticed that there's some relations between numerators, very much like I just showed you a 2-looping QCD. And it didn't quite work. There were some exceptions, but it looked to be similar to Jacobi identities. So it's pretty simple. Once you know what you're looking for, then it's not hard to find. So if it exists at loop level, if there's something here, it must exist at tree level. Where else did it come from? Right, from unitarity, loops are built from trees, so therefore it had to be there. And you could say this might have just been some random curiosity, but I think, as people know in this workshop, there's been many talks about double copy. This was not an accident. It showed some kind of fundamental structure for gauge theory and its relationship to gravity. But if you want to go from gauge theory to gravity, you replace color factors with numerator factors once the Jacobi identities are satisfied. And that all came from the data. It's not like one day we woke up and said, aha, look, there's color kinematics, right? It came out of the data. And where do this past success, where does it come from? And it's basic principles. First, amplitudes are smarter than we are. We use data as a guide. We should take inspiration from real world physics. We should be thinking about problems related in some way to the real world. The gravitational waves, of course, a perfect example of that. When you encounter a curiosity, you need to always make a judgment call. Is this an accident or is this profound? Right, so you put a little effort into that. Sometimes it's just a curiosity and forget about it. Other times it's not, and you should really pursue that. The other thing, we need to find connections to other subfields. That keeps our field healthy. This is how we're going to survive another 50 years, right? We're going to keep on reinventing ourselves, finding connections, finding things that are interesting, not just to us, but to other people. We have to find new structures. We should make bold guesses, but always, if you're going to make a bold guess, be ready for the David Grosses of the world who say, show me the evidence. Why do you say this is true? And of course, we need to push the state of the art. That's the way we know that we're making real progress, that it's not just some fake progress of some kind. Now, let me just finish up. I'm almost done. Let me just finish up with just a couple comments about the future. I think there's some directions that we should look at, maybe a little more thinking about. They're just opening up directions that I think that more effort should go into. One is SMEFT and one is the bounds from the EFT coefficients. So just a quick comment about the standard model EFTs. So we all know why this is being done. It's because BSM physics is very hard to find at the LHC. So you approach it with an open mind, use effective field theories to quantify the physics beyond the standard model, but you do it in a way that's agnostic to what the new physics is. And these topics are, this topic of SMEFT and HEFT, they're becoming much more popular. And as you already heard, the idea is you take the standard model, you add higher dimension operators. And one of the examples, I think a good example of structures, we're looking for structures. A place where amplitudes-based approaches can really help is to try to understand the structures of the scattering amplitudes in SMEFT. And what Alonso, Jenkins, Manahar, and Trott, what they had found by looking at the anomalous dimension matrix of these operators, this is dimension 6 operators in SMEFT, is that there's a lot of zeros. And to them, it looked mysterious. It was a pattern that was analogous to supersymmetry, but it still looked hard to see in the sense that they couldn't see it in their Feynman diagrams. And this was explained very nicely in the Chung and Chen paper. What they pointed out is by looking at the unitarity cuts, so you're looking in an on-shell way, you can identify these zeros as being connected to helicity zeros. And this is something we know very well. And they were able to explain lots of new zeros. And in fact, what's kind of amazing, this is something that we found, is that it's not the end of it. You might think that all of this magic would only happen at one loop, and that's because you're feeding trees into it, and there'd be no more zeros, and that's the end of it as you go beyond one loop. But in fact, there's an infinite sequence of zeros that appear at all loop orders. And these are unobvious in the sense that if you did it by Feynman diagrams, you'd find Feynman diagrams exist. Nevertheless, it cancels. And there's an opportunity here. So besides helping with cross-section calculations, there's new structures to be uncovered. And this is one example. Another example, I think, for the future where we can do a lot in our field is the EFT coefficient bounds. And we heard a few talks about that. And the question is, what EFT coefficients are physically allowed? And this is right up our alley. Well, first of all, you want to do it in a scattering amplitudes context because that way you're gauge invariant. You're avoiding issues with field redefinitions, gauge fixing, unitarity, crossing, dispersion relations. Those are the natural tools for finding the bounds, as we heard in these various talks. And there's really an opportunity here, for people to think about. There's, I think, really a lot of exciting stuff that can be done. And one of the things that we did, so there's a recent paper we had with Dimitris and Sasha, was we looked at data, right? We've learned our lesson for the past. We're supposed to be looking at data. Well, what does the data tell us? What do the amplitudes tell us? And we generated new data by looking at field theories with massive particles in the loop, consistent field theories, and trying to understand where in the low energy EFT, where you're well below the mass of the particles circulating in the loop, where do you wind up on the plot of the allowed Wilson coefficients? Okay, these aren't exactly Wilson coefficients, they're amplitude coefficients. And the answer was in a tiny, tiny place. Now, you could say, okay, that's just some accident. I mean, it's a curiosity, what of it? Or you might say that this is something very profound, something that we need to get to the bottom of, something that we need to understand why these constraints are so loose are there more information that we can gather from looking at the scattering amplitudes more generally than just the 2 to 2? Now, of course, I believe that this is not just a curiosity, but this is of fundamental importance. On the other hand, of course, there's only one way to find out. We have to get the proof. And that I leave for the future. Let me just wrap it up by saying, following these principles, these basic principles that we discussed, that these lessons from the past, I am very confident that the field will continue to thrive for many years to come. Okay, thank you.
Thank you very much, Zvi. Fantastic talk, very upbeat. Let's hear if there are some, first in applause. And any kinds of comments and questions or whatever. Let's hear it. David, you're first, I think.
Thank you. Thank you for those words of wisdom. I won't try and repeat any of them. I take them to heart. I want to make 2 short comments. One I made after the award of the Sakurai Prize in 2014 to Zvi and David. And there I thanked them when I spoke at Brookhaven afterwards for keeping faith in quantum field theory. That was quite hard to do for several decades in the United States of America. It was easier to do in the former Soviet Union and in Germany. So thank you for keeping faith in quantum field theory. Second comment is, we seem to live, if we are people who have mathematical expertise in perturbation theory, in the best of all possible worlds. We have 2 types of colliders, colliding hadrons and leptons, and supersymmetry, extra dimensions, weird and wonderful effects don't appear in those. I remind you that this development in perturbation theory was supposed to be something done by boring plumbers who just calculated the standard background, standard model background, and then the new physics was emerged. The new physics hasn't emerged, so the demand for high precision calculations persists. And then this wonderful connection, which I've really seen dramatically reinforced in this conference, shows that mathematical expertise which were required to develop for particle physics colliders also apply to hadron colliders. So whilst there's a lot of moaning and tearing of hair among people that were committed to bold, grand new ideas emerging, we're actually in this very happy situation that there's a long-standing future for conferences of this type, directly addressing to empirical questions provided by the 2 types of collider with which God in her wisdom provides us.
Yeah, thanks. That's very nice.
Hey, can I add something?
Sure.
Thanks a lot for that great talk. It was great to take a walk down memory lane there. It was also great that you referred to lessons for all the younger people, because most people don't know this, but I'm a year younger than Zvi. So I was hearing myself there. But anyway, one minor timeline correction, which is when we did ABDK and BDS, the Weisert, Eden, and Staudacher formula for the cusp anomalous dimension wasn't known yet. It only came in 2006, and those papers were like 2003, 2005. In fact, I was rechecking the BDS abstract, and we only barely kind of knew the 3-loop cusp anomalous dimension. It was based on the maximal transcendentality principle by Lopatov and collaborators in translating from the QCD result. So,
well, as it turned out,
we didn't know it. We didn't know that piece to all orders.
But as it turned out, BDS sat there for a while until one came along. So it didn't
nobody
really
had
matter.
paid that much attention to it until 2007.
Exactly.
And by that time, BES was sort of established.
That's correct. Yeah. By the time it actually mattered, BS was there. Absolutely. Yeah, I forgot. I should have looked.
I have a little story about Ed and Twister Strings. I didn't like meet him directly and talk to him and inspire him in that direction like maybe David did, but at one point I got an email from him and he says, I've been looking at this 6-point formula in the literature, and I was wondering, is there any like typo in it or something? And so then I like typed it in, and I said, yeah, maybe you should flip that sign. And he said, oh yeah, thank you very much. And then like a couple of weeks later, he comes back and he says, there's this formula at 7 points by Berends-Giele. I was wondering if there's any issue with that formula too. Now this formula was like 2 pages spread out over nuclear physics B, and okay, I can type pretty fast if I have to, but so I did, and I typed it all in, and I checked it against other stuff I had, and it was all fine. But then I remembered, oh yeah, they use the opposite sign convention on the those square brackets. So I told Ed about that, and he said, oh, thank you. So I had a pretty good inkling that something pretty fantastic was going to happen pretty soon.
I think the other thing you can learn from that is Ed does explicit checks like the rest of us.
Ed is, he might write papers that have 100 pages and no equations, but underneath he's pretty hard-boiled. He is very hard-boiled. Thanks again for your talk.
Nima, you have a question, comment?
Yeah, I just had a little comment. First, that was really beautiful talk, Zvi. I really enjoyed it. As you know, I really love this history and the story, which I think is just fantastic. But I couldn't resist saying something now that Amplitudes is a respectable field with 100 odd some people showing up, 150 people showing up to these meetings. There's something I think striking about this history. Which is, I think, also true of many other very important developments in theoretical physics more broadly, and something which is, I think, not appreciated by many of the people. Some of them old fart physicists, some of them pompous historians of physics, and so on. But since it showed up so often in your story, I just wanted to say it explicitly. When you have a sort of biggish field, it just naturally happens that many people work on a relatively small number of things. But it's very striking in your guys' story how much of the progress had nothing to do with what everyone was working on. And that's, of course, part of the standard story that we like to tell, the sort of heroic story of the lone person in the corner ignoring what everyone else is doing. But that's also not what happened. What happened was this fantastic intermediate thing with a small number of people knowing something amazing was going on and getting to talk to each other and interact with each other, even when, maybe not many other people knew what was going on. But I think this sort of intermediate thing of small collections of people realizing something fantastic is happening and just going to town on it and screwing everyone else, that's the way real progress happens. When fields are born and then you want to, really clean things up and, make everything perfect, then is great. Tons of crowds of people are wonderful for that. They're not good at coming up with really new ideas. And nor is it just a lone person in total isolation either. It's this really cool intermediate collection size of people who see something and go for it. And you guys did that. It was massively inspiring. It continues to be massively inspiring. To me, to all of us, but I think it's also a very interesting, more general lesson to think about, and also to guard against a little bit the sort of more boring aspects of a field with lots of people doing very similar things.
Yeah, thanks a lot, Nima. Maybe just to emphasize a little more, of course, we were talking among ourselves, but we were, of course, paying attention to QCD, outside the field. That was also very important.
Julio, comment?
Yeah, just a very brief comment. So thanks, Zvi, for telling us the story, some of which happened before I was even born. But, I was going to say that as your former student, I couldn't help but notice an omission of one of the lessons that I learned from you, which I think is very important, which is the following. It's almost impossible to convince anyone of anything. The only thing that works is I've done the calculation and this is the result. And I think that that is a very healthy thing that is done over and over in Amplitudes and not in other fields. Yeah.
So as you can see, I wasn't just making it up. It was actually based on real experience of trying to convince people of things, and it's just impossible. And you get all sorts of objections that in retrospect don't make much sense, but you just can't make any progress until you've actually done the calculation that demonstrates a verification or going beyond the state of the art. Absolutely.
You know, I had a bet with myself that you would have had bottles of wine in this talk. I lost myself a bottle of wine by not taking that bet.
That reminds me, I am owed a bottle of wine still.
Doesn't that make bottles of wine appear in this talk? So you win or lose.
Oh, okay. I guess I beat myself after all.
Right. Yeah, I guess I could have used that, but it's okay.
Hey, Zvi, you know that quote on the slide you have there?
Yeah.
I used this once or twice in some frontispieces of some talks, and at some point, Roger Blanford said, you know, Kip Thorne and I are writing up a book on classical physics, and we would like to use that as the start of one of the chapters. So can you tell me what the provenance of that quote is? I said, well, I kind of got it from wiki quotes.
Yeah, that's where I got it from.
So then I contacted Misha Schiffman, who edited a book on Landau one time. And Landau first said, Schiffman first said, yeah, that sounds kind of reasonable, but let me do a little more research. And then after a few weeks, he came back and he contacted a Russian historian, maybe at Brown, who said, no, that doesn't sound like Landau. And I don't know of any place where he actually said it. So then they didn't use it in their book. And then like 2 months ago, I heard from a guy from MIT, and he asked me about this. And I said, I don't know, here's a history of what I tried to find out. It doesn't seem very good, but he dug around on his own, and then he's like found a lot of evidence. I mean, he found a book by Landau's niece in which this is quoted. So now I think it's genuine again.
I see. I was about.
Was that David Kaiser who looked into this at MIT? That guy?
Let me check my email. You know him?
Yeah.
No, it's a guy named Dan Roberts. He's not in physics at all. I think he's in engineering of some type.
Well, there's this very mean saying about Landau and Lifshitz, which is that.
Sorry, he's a physicist turned AI researcher at MIT, he says.
I see.
So what were you saying about Landau?
I was just saying that there's a very mean saying about Landau and Lifshitz, which is that it's a series of textbooks where every word was written by Lifshitz and every idea was contributed by Landau. I wonder if something. I wonder if that's relevant.
You just muted yourself, or somebody muted you.
Oh, yeah. Okay, good. Yeah.
I have a comment to make about that. My extensive contacts in Russia and the Bog-Lyubov school, and I greatly respect them, but I have heard something about the Landau school from older people. And Landau was famous for turning up at a seminar, interrupting people in a talk, coming out with some great new idea, going off and coming back a week later saying, yes, it's exactly what I said. But he cultivated what in England is called the air of effortless superiority. You know, the picture of him lying on the sofa is the epitome of the great thinker. But in fact, in private, all the time he was calculating. And so between the great big idea and either saying, yes, it's like that, or it's different, but even more interesting, there was going on that same calculational intensity of implicitly, hiddenly, that was going on explicitly in the Bog-Lyubov school.
Okay.
Yeah, I don't remember where I remember this from, but it's I quote it sometimes to my students. Landau would write 50 pages per day, 50 pages every day.
Of what?
Of various calculations. Various calculations going through the papers. That's a number I don't remember now the source of this, but that's, yeah, 50 pages a day.
So as the chairman of this session, I just want to say that you know, we have to cut it at some point because it's also going to be uploaded to YouTube, and it's great that the discussion can continue afterwards. And so we're definitely not closing the Zoom link, but maybe this is an opportunity to thank Zvi again for all the work you put in, and of course the fantastic story that you could tell us. It was really great. So thanks a lot, Zvi. That